you see this screen? Okay, I'll start.
We can't hear. Yeah. So, you need to share and then share sound.
Huh?
Okay.
So just stop sharing your screen. So that's it. Now when you open this share screen dialog,
Yeah.
the dialog will be open. Before you select the window that you're going to share us with, in the bottom left hand corner there's a checkbox that says share display sound.
Oh, okay.
So
Sorry.
you've got to tick. That's all right. You've got to tick that before you then select your window you're going to share with us. Okay.
My
It's all
bad.
right.
We have decided to choose
That's better,
question
thank
3
you.
for our group
Is
project,
that good?
Yep. Perfect.
which we will explain about why the derivative of a volume of a sphere is the surface area. We have used several methods to prove its question, such as the first principle of derivatives, and also found a few examples of more shapes that have the same occurrence, such as a cube and cylinder. We have also shown that how this holds in another dimensions, such as circumference and an area of a circle.
From the question given, it is clearly evident that through the derivation of volume, we will receive surface area. This can be seen in this short section of working, where volume has been differentiated with respect to r, which is the radius. So why is surface area the derivative of volume? For our first proof, we take a sphere with radius r. For the sake of this proof, let's paint the outside of it blue. This would be representative of the surface area of the sphere, due to the fact that the paint covers the entirety of the outside. We can delve deeper into this by involving the first principles of differentiation. As the paint layer will have a certain amount of thickness to it, which is negligible still, we can give it a value of h for height. Due to its negligibility, we can use the limit as h tends to 0. Essentially, we need to prove that the volume with respect to r plus h minus the volume with respect to r would leave us with only the volume with respect to h. This answer would be the surface area. So if we actually execute this and substitute volume into the first line, we get what is on the bottom line on the screen.
We're going to have pizza and ribs tonight?
Oh, cool.
I didn't say we were, I said are we?
We are left with this bottom
I thought
line
you said we're having
after some
pizza
rigorous cancellations.
I was asking.
tonight.
As we are still left with the limit as h tends to
I
0,
haven't got any money,
we
so
can
I don't
take
know what I'm asking.
the second and third subjects to be 0. This leaves us with just 4 pi r squared. This is the surface area of the sphere, thus proving the question.
I'll try again in
In
an hour.
relation to this proof, we can also bring the meaning
I said I
of
will try again in an
differentiation.
hour.
If we are
No,
to
we say no, okay.
differentiate something, we find its rate of change. In this
You
case,
can wait.
the paint that we
You got some
mentioned
fat
earlier
reserves there?
represents the rate of change
Like
of
me?
the sphere's volume, as it is, in a sense, getting bigger and bigger because of the new layer of paint. Therefore, surface area is the derivative of volume.
Since the volume of the sphere is 4/3 pi r cubed, and we know that r is the independent variable, we may differentiate the volume with respect to r. Let's say that we have a sphere with radius r. Then, by slicing the sphere horizontally as many times and as thinly as possible, we get multiple circular surfaces that vary in different radii. The red outline represents the diameter of the sphere. Afterwards, as we stack the circular surfaces on top of one another by decreasing radius, we get something that resembles the shape of a cone. The diameter of the sphere, which is the base of this cone, has the area of 4 pi r squared. This corresponds to the surface area of the sphere. This is because this cone was originated from the surface area of the sphere, that surface area being 4 pi r squared. Since the height of the cone is r, the volume of the cone is equivalent to the volume of the sphere, as it is 1/3 times 4 pi times r squared times r, which results to 1/3 times 4 pi r cubed. Therefore, the derivative of the surface area of the sphere equals to volume of the sphere.
So now that we have proven this, does this hold true in other dimensions? In this case, let's use a circle with radius r. We know that the area of it is pi r squared, and its circumference is 2 pi r. If we are to differentiate the formula of the area of this circle with respect to the radius, we get the circumference as we can see here. This provides evidence that this does hold true in other dimensions. Now that we have proven that the surface area is the derivative of volume, using a sphere as an example, as well as its application in another dimension, we would like to prove how functional it is when we take into account other shapes. Let's take a cube. The volume of a cube is r cubed, where r is the side length of the cube. But if we were to take the derivative of this, it would mean that the surface area would be 3r squared, which we know is not true. We know that the surface area of a cube is 6r squared. So why is this? Why is the surface area not the derivative of volume for a cube? Simple. Earlier we mentioned that r should be the radius. If we take the midpoint of the cube and draw a line to the middle of one of these faces, this can be the radius of the cube. This gives us a new volume to follow, which is equal to 8r cubed. This is because technically there are now 8 smaller cubes within the large cube, as it has been split up by the radius lines, as we can see in the diagram. If we differentiate this, we receive 24r squared. Now if we take one of the faces of the cube, we can see that the area is 4r squared, as each side length has 2 of the radii. Following on, there are 6 faces, and thus the surface area should be equal to 24r squared. This was the derivative of volume that we had just found. So from this, we find that the derivative of volume being surface area is a functional application to other shapes. Just to be safe though, let's try another shape. How about a cylinder with radius r and height h? We know that the volume is pi r squared h, and that the lateral surface area is 2 pi r h, lateral surface area being the curved surface area between the two circles. If we are to find the derivative of volume for this cylinder, we receive 2 pi r h, which is its lateral surface area. Thus it is evident that the surface area is a result of differentiating the volume of a 3D object. In conclusion, we have successfully proven that the derivative of volume for a shape is surface area. We have also concluded that this does hold true in other dimensions through our use of a circle as an example. After this, we have reached an agreement with our corresponding examples, which were the cube and cylinder, thus proving our claims in answer to this question.